All right, let's just dive right into this explainer, shall we? Today, we are unpacking a notoriously difficult logistics puzzle. And I mean, this thing impacts almost every hidden layer of our modern lives. Whether it's optimizing the microscopic, complex traces on a computer circuit board or routing some massive global delivery network, we are constantly slamming into a fundamental mathematical challenge. So we're going to explore exactly why pure perfection is sometimes mathematically impossible, and how computer scientists use some absolutely brilliant workarounds to keep the whole world running. So what is the shortest route to visit everywhere exactly once? It sounds super simple on the surface, doesn't it? Like, if I gave you a handful of points on a map, you could probably just trace the shortest path right there with your finger. But this very question actually reveals a terrifying computational reality. Because when you scale this problem up past just a few dozen cities or delivery stops, finding the absolute best, most perfect answer becomes a monstrous task that will literally break the most powerful supercomputers on Earth.
Okay, here is a roadmap for today. First, we'll cover the traveling salesperson problem itself. Then, 2. The factorial explosion. 3. The Bellman-Held-Karp algorithm. 4. Minimum spanning trees. And finally, 5. The metric TSP shortcut. Let's get to it.
Section 1. The Traveling Salesperson Problem.
Let's look at the incredibly deceptive trap of the core problem itself. In math terms, the Traveling Salesperson Problem, or TSP, asks us to find the most efficient way to connect a network. Imagine every location, we call these nodes, is connected directly to every other location by a path or an edge, and each path has a weight. Just think of weight as the distance, the time, or the cost to travel it. So the TSP essentially asks us to find a complete loop that hits every single node just one time, finishes exactly where it started, and does the whole shebang with the absolute minimum possible total weight.
Section 2. The factorial explosion.
Now, you might be asking yourself, well, why not just calculate every single possible permutation of the route, write them all down, and just pick the shortest one? Simple, right? Well, actually, no way. And that's because of factorial scaling, which is represented as omega of n factorial. Believe it or not, finding the perfect route this way could literally take longer than the universe has existed. Think about a naive algorithm that just generates every possible sequence of cities. For 5 cities, that's 120 routes. Totally easy. For 10 cities, it jumps to over 3.6 million routes. Still somewhat manageable for a modern computer. But for just 60 cities, the number of possible routes is a number with over 80 zeros. Even if you checked a billion routes a second, the universe would end before you ever finished. This is the factorial explosion. It is fundamentally impossible to brute force a large TSP.
Section 3. The Bellman-Held-Karp algorithm.
So, if the naive approach takes a literal eternity, how on earth do we fix it? We clearly can't just check every single path. Well, enter the Bellman-Held-Karp algorithm. By using a really cool technique called dynamic programming, this algorithm cleverly breaks this giant monster of a problem down into smaller, overlapping subproblems. Instead of calculating entirely new routes over and over and over again, it figures out the shortest paths to smaller clusters of cities, subsets, and then just stores that answer. Then it essentially builds the final route by looking up those smaller optimal subroutes. I mean, think about it. If you already know the absolute best way to visit a cluster of 5 specific cities, you don't need to recalculate that exact part of the journey every single time you test a new global route that happens to pass through them.
And this represents a massive theoretical leap. We are moving from a naive runtime of omega n factorial way down to the Bellman-Held-Karp runtime of big O of 2 to the power of n plus little o of n. Now, while both runtimes are undeniably huge, calculating in exponential time is a vastly superior solution to a factorial explosion. To put that into perspective, 2 to the power of 60 is a genuinely large number for sure, but it is fundamentally smaller and way more manageable than 60 factorial. We have essentially dragged a completely impossible problem back into the realm of theoretical possibility. But you knew there'd be a catch, right? The absolutely crucial point here is that while we save time, we pay a massive, massive price in exponential memory requirements. See, to avoid recalculating all those subroutes, the algorithm has to maintain a giant lookup table in the computer's memory. And as the number of cities grows, the size of this table grows exponentially. Very quickly, you just simply run out of RAM. You might theoretically have enough processing time to run the algorithm now, but literally no computer on Earth has enough memory to store the table for a truly massive network.
Section 4. Minimum spanning trees.
Okay, so brute force takes way too much time, and dynamic programming takes way too much memory. What if we just admit defeat on getting the absolute perfect route? What if we just need a really, really good one? Well, welcome to our practical workaround using minimum spanning trees, or MSTs. An MST is fundamentally different from our salesperson tour. It doesn't actually need to be a single continuous loop. It just needs to be a branching network, like a tree, that connects every single node together without any closed loops, all while using the absolute minimum total wire or road or cost. And here is the truly beautiful part. Unlike that impossible TSP loop, we can solve for an MST optimally and incredibly fast. We can use highly efficient greedy algorithms like prims or Kruskal's to calculate this optimal connected backbone in a tiny fraction of the time. They just look at the cheapest local connection step by step, and mathematically, they are absolutely guaranteed to find the perfect spanning tree. It's a real game changer.
Section 5. The Metric TSP Shortcut.
Now, how exactly do we turn that branching tree back into a continuous loop for our salesperson? To pull this off, we need to operate in what's called the metric TSP. This is a special case that beautifully mimics the actual physical world we live in, where edge weights obey something called the triangle inequality. Just think about it naturally. Driving directly from city A to city C is always going to be shorter, or at absolute worst, equal to taking a detour through some other city B. When this fundamental physical rule applies, it unlocks a seriously powerful mathematical guarantee.
Number 2. That is the maximum penalty factor we pay when using our shortcut instead of stubbornly trying to calculate the absolute perfect route. Let me break down exactly how this incredible guarantee works. So we know for a fact that if you take the perfect, impossible-to-find TSP tour and just delete one connection, you get a spanning tree. Therefore, the perfect TSP tour must be longer than, or at least equal to, our minimum spanning tree. But here is the really clever trick. If we essentially trace our finger around the outside of that branching minimum spanning tree, basically walking down every branch and then walking back up it, we have visited every city, and we've traversed every edge of the tree exactly twice. Now, because of the triangle inequality we talked about, if we just skip a city we've already visited and draw a straight line to the next unvisited city, the route actually only gets shorter. We do this using a simple depth-first search, or DFS, which honestly just means following a path down a branch as far as it possibly goes before backtracking. So by simply combining our blazing fast minimum spanning tree with this search, we are mathematically guaranteed to generate a highly efficient route. And the absolute best part of the whole thing? We can mathematically prove this route will be no more than twice as long as the impossible perfect tour. And in reality, it's usually much, much closer to perfect than that.
It's pretty wild to think about, right? We basically completely bypass the problem that would literally outlast the universe, just by accepting a solution that is mathematically guaranteed to be good enough. As we wrap up this explainer, it really leaves us to wonder, what other impossible computational quests run our modern world using brilliant, good enough approximations? Because sometimes the most elegant math isn't about finding the perfect answer at all. It's about perfectly defining the boundaries of what is even possible. Thank you so much for joining me for this explainer, and keep questioning the algorithms that run our world.